if we were to do the same thing here, if we were to go back, so convert this F or hex representation to binary, we get something like this. Let's say we get a, let me just format this a little bit. Okay, that seems fine. Okay, that looks good, aligned. So if we take that and put it right here, but in this case we have 3, a D, a 2, 0, 0, 0, 0, 0. So what does this 3 represent in binary? So that's just 0, 0, 1, 1. Does everybody agree with that? If you don't, get a pen and paper and do it, because this represents 1, this represents 2, so that's 2 plus 1, that's 3. This represents 4, and this represents this one represents 8. Right, so that's a 3. Now what's a D? So A, B, C, D. 10, 11, 12, 13. How do you get 13? You gotta add 1 plus 1 more. That's 12, 0, and then that's 1. You got a D. Then how do you get a 2? So that's 0, 0, 1, 0. That's a 2. How do you get 0? Well, that's easy. It's easy, right? Yeah. So this is what we get from this. Pretty easy so far. So now what we have to do is we have to take this format. This format is actually like this. So 1, 2, 3, 4, 5, 6, 7, 8, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3. So if you add all of these up, these are 32. If you discard these 2 spaces, I have selected 34, discard these 2 spaces, we have 32 ones, right? And that's all adds. So this first one, so actually if you see it on a computer, it should be like this, right? But the format says we got to split it like this when we're visualizing or doing any calculation. So the first one represents a sign bit. The 8, these 8 ones that I had selected right here, they represent the exponent, and the rest of the 23 are the significant, which means in our case right here, what is that? That's a sign bit. That sign bit says it's actually plus, right? 0 means plus, 1 means minus, which is kind of, I don't know, works. Okay, and now after that we need to take 8 of these. So we put a space and then we combine these. We get how many? 1, 2, 3, 4, 5, 6, 7. We need 1 more from this group. So we're going to split it like that. So right here, as I selected, you can see 8 of them are selected. So we take these 8 and convert them to decimal. If you're not good with conversions with decimal to binary and binary to decimal, please go ahead and review that, because you're not going to understand any of this unless you know that. So we take this, convert that to decimal. What do we get? So this first place represents 1, second place represents 2. So we're going to do the calculation here. 2 plus, this represents 1, 2, 4, 8. So we have 8, and then we have 16, 32, and 64. So 8, 16, 32, 64. And I suck at calculation, so I'm just going to use my calculator. off the screen. 2 plus 8 plus 16 plus 32 plus 64. That gives us 122. Right? So this exponent is 122. Now, if you look at the IEEE format, you can clearly see you always got to subtract 127 from it. It's just a rule. Get that in your head. Right? So we do that and we get -5. So our actual exponent of this number right here, of this, is -5. That means our decimal is actually small. So we'll come back to that later. Now we're going to take this and convert this thing, this significant, to, we don't actually need to do this, but we're just going to do it for fun, to decimal. So what this represents is, let me show it here. So 0. So actually in the book he has a pretty good representation. I actually like his book. It's pretty good if you actually listen to his lectures. I highly recommend it. Okay, right here. So this is how we start it, and then we're gonna start with this. So after the decimal, which is what the significant is, basically there's a dot right here. So that's what it represents. So the first bit is 1.5, second is 1.20, 0.5. This is 0.25. This is whatever this is, 1 divided by 8. So how many ones do we have? We have all zeros except the second one. And what is the second one? Well, the second one is 1/4, which is 0.25. So that basically means this entire thing represents 0.25 literally, and that is it. This is before the decimal, this is after the decimal. So two conversions are different. You don't think of this as 1, 2, 4, 8, 16, 32, 64, 128. No. This is after the decimal zone. So after 0, right? We got to think opposite. We can't think this way. This is something else. This, you can use this to count exponents. We got to count decimals right now. Significant. So basically, what this number is, it is plus 1.25. Now, this 1, where did that come from? Well, keep that in mind. That's called the fucking mantissa, or however you say that. It's a mantissa, and it is always implied, even if it's not there. It's not here, it's nowhere here, but it's implied. And because how they decided to make this format, and this format is pretty genius if you guys ask me. So basically we have 1.25 positive times 2 to the -5 exponent. What does that mean? That means we're going to take this point right here. So I'm going to ignore the plus sign. So we have 1.25. So we're going to take this, right? This and this is basically the same thing, right? It doesn't matter how many zeros I added before, or it doesn't matter how many zeros I add after the decimal place. It doesn't matter, simple math. But now we're going to take this and move it 5 times to the left because it's negative. If it was positive, we got to move it this way. But this time we got to move it the other way because it's negative. So we're going to select that, move it 1, 2, 3, 4, 5. Right? We do it the extra 0, and we get that number. So basically, this is same as this. This is the hex 32-bit hex representation of IEEE-754 float number, which is equal to 0.0000125 in base 10, the decimal, the one we are used to, right? So that's how cool it is. But like, how do we print the binary? Well, binary stuff is even easier. This is even easier than this because we don't need to do any of this shit. All right, we can get rid of that. We don't even need to convert this because that's confusing. All I need to know is this exponent and this sign. That's it. So what I can do, so how do I represent the binary representation of float from this number? Well, like I said, the mantissa is always implied. This thing, the mantissa, right? He did make a mistake and I did correct him. This is actually not a mantissa. This word is supposed to be the significant. He did correct it and he still missed it. Right here, significant. Mantissa. Where's the mantissa? Right here. We have this. So this mantissa is implied. Exponent we just found out. Right? So mantissa, point, all of this significance. Right? So we're just going to copy that. And these always should give you the 23. If you don't count these empty spaces that I put in just for formats, that's 5 spaces. So 28 selected minus 5, that gives you 28 bits, right? Right there. So if I delete this spaces, after the decimal, I should have 23 numbers. As you can see, 23 right here. So that's that. Now, it says exponent is -5. So this is that times 2 to the -5, right? But we can't do this. We don't want this. We want the actual representation. We don't want any scientific notation. So what we're going to do is move the decimal 5 times to get rid of this. So if I just copy this over, delete the 5 times, add a couple more zeros, and if I take this decimal, move it 5 times, 1, 2, 3, 4, 5. That's the answer. That is what we should get if we put in this number. So actually, let's do it. So I take this, I run my program. Wait, no, that's not the right program. cd into csci 4663, and then cd into assignment 1. And then I run my program, and then enter the number, and copy all this, paste it right here. It should match exactly. Let me get rid of the sign. See? Same thing. Alright. So that is it. That's all we have to do. Now let's look at an example where the exponent is actually +5. Then what do? You delete that. Let's delete these two. So now let's take this one and move it 5 times. 1, 2, 3, 4, 5. There's the answer. We can get rid of these. It's pretty simple. But here's the thing. What if we have this more than 23 times? So we have 24. How about that? So we need to move this 24 times. So if I move it, we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 23. And then I still need to move it once. That's 23 times. But I still need to move it once. So what do? I just add an extra 0. put a 0 at the end, do this. That's it. What if I need to do it 25 times? Add an extra 0. Okay. What if I need to do it negative 24 times? Let me pick a smaller number. Negative 10 times. Well, all you have to do is just add more zeros. Take this, put it at the end, and shift this 10 times to the left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I don't need those. That should be the answer. That's basically it, guys. Now, you're going to ask me, well, how do I get this? How do I get this? And how do I get the sign bit? Well, we use the things called masking, bit masking. So, and he taught us this. That if you don't feel comfortable using bit masks, just go watch his lecture video. The last one should cover it to see the bitwise operator. So if I have int 32, I just do u x, and then I need to import. What is it? I think it's cstd int. Yeah, fuck it. Okay, so get the x. Let's just, we're not going to do any inputs. We're just going to set it ourselves. So we're going to do 0x and then this right here. Right? All right. And then if I want to get int 32-bit t is equal to exponent is equal to, let's do sign first. That's going to be easiest. Sign. All right, so here's a rule that you guys should know before using bit masks. If I do 0, 0, 0, and then AND it with, if I have 0, 1, 0, and if I AND that with 0, 0, 1, what am I going to get? Does anybody know? If I AND anything with a 0, I'm going to get a 0. So that means these two places are definitely going to be 0. But here I ended with 1. So a number ended with 1 is going to give me this number. So in this case, it's a 0. But if I had this, if I had that number, then 1, a number, doesn't matter, 0 or 1, ended with 1 gives me 1. Right? So I want to get the sign bit. So in this entire, let me copy this again. In this entire thing, I have 32 bits. So I can have another 32 bits. And if I select all this, I should get 34, including 2 spaces, 34 right there. So if I want to extract this number right here, all I have to do is AND this number, this whole number, by this number, and change the bits to 1. Let me just show you this, because my English sucks. I can't explain. So if I AND this, and if I put a 1 here, whatever number is here will show up as a result. So this will be like 1 and then a bunch of zeros. Just take my word for it for now. Right? If I put a 1 here, then I'm going to get 1 right there. That makes sense. If I put 2 1s here, I'm going to get 2 1s right there. Everything else will be 0. It doesn't matter if this is 0s or not, right? I'm still going to get zeros because a number ended with a 0 gives me a 0. A number ended with a 1 gives me that number, even if it's a 0. So if this is 0 ended with 1, I get a 0, right? Cool. So what do I want to do? I want to get the signed bit, right? So the signed bit says, signed bit is the first bit ever, right? I don't want to get anything else. I don't want to get exponent or anything else. I just want the signed bit. So what I want you to do is I'm going to take this number. This number is what? That number is all the f's. I'm going to take that. I'm going to end it with this number. What is this number? Right? What is that number? So we're going to take that number. I'm going to split it into groups of 4 that you guys can understand. Right. 1, 2, 3, 4. 1, 2, 3, 4. Right? That's the same number as this right here. I just split it into different groups of 4 so you guys can understand. So this, what is this number right here? That's a definite 0. What's this number? 0. 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 This 0. What is this number? Well, this place, this first 0 is a 1 place, this is 2, this is 4, and this is 8. So all of my zeros except the 8th place. So that's just 8 plus 0 plus 0 plus 0, which is 8. So this bit mask right here, 800000000 should give us the signed bit from any hex representation. If I do it with this one, it's going to give me a 0. So if I take this sign, so I take x and I end it with 8, 1, 2, 3, 1, 2, 3, 4. That will give me the signed bit. If I do C out, if I save that, Control D, clear, CD, 2 directories, desktop, G++, hello CPP. Then I do // save that out. See, the signed bit is a 0. If I want to test that theory, when should I get 1? If I have all F, if this is an F, I took that from here, that should give me the first letter is a 1. So if I do that, if I rerun the program, ooh, what happened there? I just need to do Boolean. Yeah, store that in a Boolean so that you don't run into signed and unsigned stuff. So that basically, so let's just change it to 3 as it was. So that's how you extract a sign. And well, now you're going to ask me, how do we extract an exponent? Well, same thing. You int 32t exponent is equal to, I'm going to take x, and I'm going to end it with another bit mask that will give me the entire exponent. So let's do this. Let's do this. Let's zero this out. Now, I want this entire exponent. I want everything else to be zeros. All I want is this. That's it. That's all I want. How do I get that? Well, I turn all of this to 1. Because a number ended with a number will give me that number right there. That's what I want, right? So what does this represent in a hex, right? Well, let's figure it out. Let's first split everything in 4 so that we can easily convert to hex. Right? So what does this first one give me? Well, that's a place. Convert this to hex. So that gives me 1, 2, 4. So that's 4 plus 2 plus 1, that's 6 and 7, right? What's this? Oh, that's just f. I know it from the top of my head. Let's do the math if you want to. 8 plus 4, 12, plus 1. I forgot how to count. 14 plus 1, 15. 15 in a hex value is f. How do I know? Because count it. Take your finger, take your hand, sorry, and count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Sorry, that's stupid. We don't count from 1, we count from 0. So it's going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. You should have your entire one hand and then one more on your other hand. So count that in hex. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then rather than going to 10, we go to A, B, C, D, E, F. So that's an F. This is an F. What's this? Well, that's just 8. And what's the rest of these? This is a bunch of zeros. So this was covered in the lecture that Ryan gave, but yeah, I covered it more in depth. So this should give us the entire exponent and nothing else. 7 F8 0 and then 4 more zeros. So 7 8 no, what was it? 7 F8 7 F8 0 1 2 3 4. That should give us the exponent. Well, let's test it out. See out exponent, and then let's run that. So what should we get? So right, this is the number. So we should get 122 as the exponent. I hope I don't mess up. Stupid. Oh shit. Why did that happen? Because I did unsigned. I need to store it in a signed, guys. Be careful with your numbers. Oops, still got it wrong. Why did that happen? I don't think this matters, but let's still do it. It's the same thing. I should get that stuff. 3D2. Well, it's wrong anyways because of this. Okay, I don't know why that's happening. X int 32t exponent. Let me see what I did. I'm pretty sure that's what I did. Yeah. Oh shit. Guys, I know why. Okay, so that's going to give us this whole thing. That's not going to give us just this, right? It gives us this whole thing, right? Let me delete this mask. This whole thing, but I need to move all of these to here, right? Because 32-bit numbers are huge. I don't want to count all the way this. I only want this number. So what I got to do is shift these. How many times? Well, how many numbers are these? 23. I need to shift it 23 times. So basically what I need to do is convert this into 0, bunch of zeros until 8 ones. Too many zeros. All right, so I need to convert this into this, right? Because when I start counting, I'm going to count from here. I'm going to count from here. So this is going to be 1 place, 2, 4, blah, 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 and this should give us this number right there. No, it won't. It won't give us that number. What the hell's wrong with me? Yeah, fuck it, let's just test it. So we do that, and then we shift it 23 times. Okay, and let's see what we get. Compile it, run it. It does give us that. Correct. So 122 times. This math doesn't add up, guys. I think I messed up. Oh, okay. It's this number. It's this exponent. And with that will give me that, and this. I was doing for quadruple 8 Fs. There. That should give us 122. And it does. Okay? So what do we need to do? We're still not done. We need to get -5 right there. We need to get -5 there. What we do is take this 122 minus 127. Minus 127. Compile it. Run it. Hey, there it is. Right there. Cool, cool. So now we're going to look at how to guess the significant. So int 32 square t significant. I don't know if that's the right spelling or not. Significant, whatever. So all we need to do to get the significant, what is the significant of this? It's this. It is that, right? There it is. So I don't want any of this. I only want this, right? So what do? I turn everything to 0. And then I turn all of these to 1s. Right? That means, well, what's my answer going to be? My answer is going to be this. All this turns to zeros. And that is my significant. I don't even need to convert that, actually. But we actually need to convert that to a hex. So what do? That's it. All we need to do is that, right? Well, yes, and okay. Yeah, so we do need to get this significant. So how do we, so we need this bit mask. We need to use this one. So how do we do that? We're going to take that, and then we're going to group that into 4. Okay, so now what is that? 0, 0. What is that? That's 4 plus 2, 6 plus 1, 7. What is that? F, 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 and F. So we got 1, 2, 3, 4, 5. 5 Fs, 0, 0, 7 Fs. So what am I going to do? I'm going to take X, end it with hex number called 0, 0, 7 F, then 4 more. That should give me the significant. So if we print that, compile it, run it. Don't actually look at that. We don't need then we need to print a hex, because this significant in decimal me has no value, right? It doesn't even make any sense. So we just print a hex value, save it, compile it, run it. That is the hex value of this. Does that make any sense? Not yet. Okay, let's make any sense. Let's make some sense of it. So we take this number and we convert that number into hex. What do we get? So first of all, there are 8 hex, right? So we need 8 of them. So 1, 2, 3, 4, 5, 6, 7, 8, and then we can just add a 0 since there's no. So 0, 0, 2, 0, 0, 0, 0, 0. So that is the number that we should get as your significant hex representation. 2 followed by 5 zeros is 2 followed by 5 zeros. There we go. We got the sign, exponent, and the significant. Now, the real part is, how do you print all the significance using binary, right? Well, the same answer for everything. Use bit masking and this. So what we do is, so when we print the significant, we better get this. Only that, nothing else. Just that, what I just selected, right? So how many bits do we need? So we're going to use a for loop, right? I don't know how to explain too much in detail of how I came up with this stuff, but I just did. Take my word for it. I is less than 23. Now you're going to ask me why 23 times. Well, we're going to iterate 23 times because there are 23 significant bits when we need to get all of them. So we're going to start with Cup, and just for the formatting's sake, yeah, do it right there. We're going to see out some stuff though. We're going to actually see out bits, and I'm going to use the ternary operators for this because they're easy. So if x, no, wrong. If significant ended with some sort of mask gives me, if it's true, which means if it returns 1, print 1. If it returns false, then print is 0. So what are we going to do here? I need a mask, right? Yes. I'm trying to, okay, let's just do it my way. This is how I did it. I declared a temporary int, right? Temp is equal to, so we need a starting mask right here. Something 1, 2, 3, 4, 5, 6, 7, 8. So this is going to be the starting mask. So the first thing we want to print is this digit right there. How do I print this 0 right there? Well, it's, if you look at the hex, it's right here. This is, it's right here. So I want to turn everything off, and I want to print, actually, yeah, okay. So I want to turn everything off and print that first significant value, because that's where, so all of this is exponent and the sign bit, right? But my significance starts after this 0, before this 0, right? So I'm going to print this first significant bit. So I'm going to turn that on and turn literally everything off. That's it. And then I'm going to take a hex value of that because I know how to work with hex values. How much is that? That is 1, 2, 4. So that's 4. And then 0, 0, 0, 0, 0. So that's 0, 0, 4, and then the rest of the zeros. So 0, 0, 4, rest of the zeros, 1, 2, 3, 4. Right there. We're going to start there. Right? So I'm going to go with the temp. Now, what do I need to do every time I run through a loop? What I need to do is move this 1 over to the right. Does that sound familiar? I need to shift 1 every time I go through the loop so that I can print every single one of these 23 bits. I know here it says 28, that's because I had these 5 spaces in the middle, but that's actually 23 bits, right? So that's easy as hell. All you do is shift right by 1. So I go temp is equal to temp shift 1. That's it. And just for the order of operation's sake, we don't run into issues, I'm going to put that in parentheses, so that's evaluated first and then assigned, rather than the other way around. So if we do that correctly, we should have this number right here. Okay? Let's try it. Did I want to print it? Yes, I did. What the hell? Oh, this is not correct. And so these two needs to be same values. I can't just print one as a character and one as an integer. Okay? So there it is. Still no. Am I compiling the correct program? Hello.cpp, hello.cpp. Oh wait, it's printing above. Haha. So see, there. Does that look similar? So if I take that value, compare it with this one, look at that. That looks pretty similar, exactly same to me. So that's how you print your significance. Now, the next issue is dealing with exponent. Like how do I know how much do I need to shift this, right? So we printed this stuff, right? Now there's always one implied right there. That's a mantissa. And in our case, we have this whole thing times 2 to the, what's the exponent? -5. -5. We can literally print that plus, right? Because the sign bit is 0. Right, blah, blah, you get it. Okay. Now, the thing is, how do you deal with this exponent? Well, the first thing we do, it's -5, so we got to move this 5 times to the left. So what we got to do is just, I'm not going to go through this, but you guys can figure this one out. So you print a plus sign, plus or minus, right? In this case, plus. And then you say, is the exponent negative? If it's negative, then you got to print a couple of zeros, at least 1 0. If it's -1, then this value becomes 0.101 and then bunch of zeros, right? Just like that. If it's -5 in our case, we need to print 4 zeros. because this we need to shift 5 times, but we only need to print 4 zeros because this mantissa counts as one of them, one shift, right? So you had to just see out 4 zeros, point 1, that's a mantissa, and then the rest of this, right? Super easy. There it is. That's the answer. If you guys, all right, yeah. If you guys want proof, I can just go into my other project. The main project is desktop CSCI 463. Assign 1, compile it. Nope. And then we're doing this one, right? Yeah. There it is, guys. Oh wait, no, what the fuck did I do? I'm so sorry. I didn't shift it yet. Yeah, so I need to shift this one 5 times. So I take this, shift it 1, 2, 3, 4, 5 times, right? And before that, I need to print a 0. So start with this. If it's a negative exponent, start with 0 and a dot, and then print however many zeros you need. So in this, so I think every time it's just going to be exponent minus 1, and then multiply that with a negative 1 so that it becomes a positive. So in this case, your loop would run negative 5 minus, or plus 1 in this case because it's a negative number. Multiply that by minus 1. That will give you 4, which means you need to print 0 dot, and then after that, run a loop to print 4 zeros, and then the loop should have this thing, exponent. Right? Make sense? Cool. That's the negative. Now, how do you take care of the positive? Well, let's just say it's a 5. So in this case, you don't need to do shit, right? So you just need to, you don't need to print extra zeros because you can just move that 5 times. 1, 2, 3, 4, 5. How do you do that? Well, what I did was I just did string. I stored this value inside a string called binary value, and then I did binary value dot insert, and then I need to give it a position, like when to insert it. So it's going to be 1, 2, 3, 4, 5. So in the entire string, this is the 0th position. So that's 1, 2, 3, 4, 5, 6. So I just need to do exponent plus 1, comma. What do I want to insert? I want to insert a dot. Or I could just do character dot. Like that. And that will insert. But if, yeah, that's what you do. But what if this is greater than 24? Remember what we talked about before? Well, in that case, what we need to do is print the mantissa, print the entire significance, and then print the rest of the zeros. Well, how many zeros do you need? Well, I can shift 23 times before needing any zeros. Actually, I can shift 22 times before needing a 0, right? If it's 23, then I need to take care of a case. Well, I moved it 23 times right there. But there's nothing else after it, so I need to add a 0 at the end. That's a special case. Or you can take care of it some other ways. But if it's more than 23, so if it's 24, then what you need to do is add another 0 and then do that, because what I just had right here, this is going to be, if this is 24, this will say do it at the 25th position. Well, if I count these are 24. I need one more 0 before I can add a dot and then another 0. So I need to know how many extra zeros I need to print. How do you figure that out? Well, that's another simple expression. Yeah, I don't know what you call it. Well, that's just going to be exponent. Minus 24. No, 23, I guess. Does that give us? Yeah. There it is. So if I just do that, that will give me exactly how many extra zeros I need to print. And then after you print all the zeros, you just run this function to insert a dot. And after you insert a dot, you add another 0 to complete it off. You guys can't play with this number if I'm wrong with these, right? So that's how you do this. I know this one's pretty hard, but yeah. All right, well, enjoy.